Hey everybody, and welcome to Chapter 17, our Introduction to Aromatic Compounds. Now, the word aromatic has some common meanings that we're going to talk about first, and then we'll get into some reactivity in this chapter, but we will see more reactivity in Chapter 18. So let's talk about what aromatic means. Just as it kind of denotes the aromatic idea, naming specifically these compounds came from the idea that they originally were isolated from fragrant oils. As we know now, a lot of the compounds that we are going to talk about are actually odorless. They don't have a beautiful smell, but the original meaning of the term aromatic came from highly stabilized compounds that were derived from fragrant oils, benzene derivatives. And so we look at these compounds, benzene, toluene, and orthoxylene here, as benzene and its derivatives. Derivative is, again, just a fancy term for saying it looks very similar, but maybe has a couple extra carbons on it. We can also call these arenes, but again, when we talk about aromatic compounds, it's not that they smell pretty, as early scientists maybe had thought. It's because they're highly stabilized. And this is where we're going to end, really talk about in this chapter is why are they highly stabilized? Just to show you where aromatic rings are, they are very common in drug design. Antihistamines, Lipitor, Zyprexa, all of these are drugs in the current market that are used for treatments of a bunch of different things, but they do have aromatic compounds in them. Coal actually contains aromatic compounds. This is a kind of picture design of what we believe the complex molecule of coal could look like. And what is important about coal is when it is burned, why we think it kind of looks like this, where there's a joining of non-aromatic and aromatic rings kind of fused together, is because we find all of these in the actual output of the burning of coal. Now, this is very, very bad for climate change because a lot of these aromatic compounds can actually become volatilized and then go up into the atmosphere. We'll talk about them towards the end of this video when we talk about polycyclic aromatic hydrocarbons. These are very bad for the environment, so that's why coal burning is not a good thing in our world, and we should try to find alternative fuels. Let's just talk a little bit about nomenclature. We don't do a lot of naming in this class, but we do need to do it for benzene and some of its derivatives, specifically so that we can communicate when reactions happen. A lot of our reactions in Chapter 18 are going to involve putting something on benzene, making a monosubstituted derivative, and then making a disubstituted derivative. And we want to know not only what the one thing we put on benzene is, but if we tend to put on something, a second thing, where does it go and what is that thing? So substituents and their relationship to each other are very important for our discussion. So tiny little bit of nomenclature. Chlorobenzene, nitrobenzene, ethylbenzene, things like that are what I would expect you to be able to know, right? We're seeing that benzene is the parent structure and the substituent is named in front. When it's monosubstituted, you do not need a number in front of that. We assume it's number one, right? We should know the nitro group and chlorine. Same thing with bromobenzene or fluorobenzene or iodobenzene if we had a monosubstituted halogen on that benzene ring. A couple of common names that we should also be aware of. Having methylbenzene, right? CH3 group. Methylbenzene would be the systematic name. Toluene is the common name. Having a hydroxyl group on there is called phenol, all right? The ether OCH3 attached onto benzene is anisole. NH2 is aniline. Having one carboxylic acid is benzoic acid. Notice how it changes the parent name of benzene to benzoic acid. Having an aldehyde on there is benzaldehyde. That's a fun one to say. Having a ketone, specifically the 2-carbon ketone right here with a methyl group and the carbon of the carbonyl. The acete group is the common name for an ethyl or an F group, so acetophenone. This one's a little bit harder, but the acete comes from the fact that there are 2 carbons branching off. The phen is for the benzene ring, and the ONE, the one, is for the ketone. The last one on this page is styrene. Styrene actually doesn't come from any functional group name. The term styrene actually comes because in 1839 it was isolated by a German apothecary who isolated the volatile liquid from the resin of the American sweet gum tree, whose Latin name styriflua. He isolated this liquid and he called it styrol. So that's where we get the term styrene from. You should know these 8 common names. All right, these are the ones that I would require you to know, not only for our communication purposes, but also for laboratory purposes as well. The only other thing that we want to be able to talk about is when we get a di substituted, right? 2 substituents on benzene. For di-substituted, we don't necessarily need to know the names, but what we do need to know is the location of the substituents on the benzene ring. All right, so I'm going to number these benzenes 1, 2, 3, 4, starting from the first one and just looking around the ring. Okay, 1, 2, 3, 4, 1, 2, 3, 4. I arbitrarily chose a methyl to start with, and I'm counting in such a way that it makes the second methyl the lowest number possible, okay? Now with these, if you have the 1, 2 relationship, 1, 2 dimethyl benzene, this is what we call the ortho position. If you are at 1, 3 dimethylbenzene, this is the meta position. Meta is the common name for 1, 3. Ortho is the common name for 1, 2. And finally, the 1, 4 dimethylbenzene is called the para position. Okay, so when we're looking at common names, once we start putting on 2 substituents, I'll be asking you, are they ortho, meta, or para in the product, right? And those, you do need to know the relationships, 1, 2, 1, 3, or 1, 4. All right. If you need a little bit of a joke to help you with that, here's one for you. Again, the 1, 3 position, ortho, orthodox. The 1, 4 position, paradox. Or the 1, 3 position, metaphysicians. Metadox wouldn't make sense. Funny. All right, let's look at the structure of benzene, all right? So in 1866, August Kukui proposed that benzene is a ring comprised of alternating double bonds and single bonds. August Kukui was an interesting guy. He was really into the artistic aspect of chemistry, which is why I think organic chemistry is so difficult sometimes, is because there's such a visual aspect to it and an artistic aspect. Kukui suggested in the structure of benzene, which is C6H6, that there was the exchange of double bonds and single bonds in an equilibrium process. And we know that now today as resonance. So resonance contributors are in equilibrium, And so that's why sometimes benzene is drawn with a circle actually in the middle to understand that those 6 electrons, the 6 pi electrons, are actually in resonance with each other, right? So equal resonance contributors, and not one location really of the carbon-carbon double bond, that it's actually a resonance hybrid, right? Because if you imagine the resonance hybrid, we would have that dashed double bond sharing location all the way around, which is how we get to just drawing a circle. Now with the stability of benzene, this is where we have this idea really bringing to the forefront of the late 1800s. Aromatic rings were remarkably stable. And so remember last semester we talked about alkenes and how they readily undergo addition reactions like halogenation shown here. This was a chapter 8 reaction. Aromatic rings are stable enough that they do not actually undergo this reaction at all with just Br2. There's no reaction there. And so it was this first realization that the stability of benzene was investigated. The stability of benzene was first investigated by looking at the heats of hydrogenation. And so looking at this one alkene, one carbon-carbon double bond, when hydrogenated, when broken, and adding 2 new sigma bonds to hydrogen, right? When we do the hydrogenation reaction, it releases 120 kilojoules per mole. With 2 pi bonds, 2 carbon-carbon double bonds, even though they're conjugated, they release almost double, right? A little bit less, probably because of conjugation, right? But negative 232 kilojoules per mole are released when we do that hydrogenation. So it was expected that 3 carbon-carbon double bonds would release 360, right? 3 times the amount that we have observed from just one. And actually, benzene is even more stable than a conjugated diene, right? It was a difference of 152 kilojoules per mole. This was the actual down here instead of what we expected. And so this is where we have to look and say, like, what the heck is going on? Why is there such an increase of stability, right? Even taking into consideration conjugation, what is going on with benzene that makes it so much more stable? It's like super conjugation, right? So MO theory can help us explain this. When we look at benzene, what we are actually looking at is a 6 atomic p orbital system of overlapping MOs. And so if we remember our MO theory from last chapter, for every p orbital that we have, right, and we have 6 in benzene, from this one from each of the carbons, for every p orbital we have the same amount of MOs. This is the MO diagram for benzene over here. We have the HOMO and the LUMO identified, right? But we do see that there are 3 lowest energy MOs and 3 higher energy MOs that are unfilled, right? 3 bonding and 3 antibonding. Now it's really these benzene orbitals and the location of the nodes in the MOs that determine how high in energy or how low they are. And it also is a lot of math. We don't need to know about those math, but what isn't really important is the delocalization of those 6 pi electrons in the 3 bonding molecular orbitals accounts for the stability of benzene. All 3, Psi1, Psi2, and Psi3, all 3 of those MOs that are bonding are filled, and none of the anti-bonding are filled at all right? So there's something to that. Not all fully conjugated rings have aromatic stability. Cyclobutadiene is actually highly reactive and has a very, very short shelf life. Cyclooctatriene actually reacts like a normal alkene. So what's going on, right? What is happening here? And that has to do with what we call Huckel's criteria for aromaticity. For a molecule to be considered aromatic, it needs to follow these two criteria, all right? The first one is pretty loaded. It needs to be fully conjugated, a ring, and has overlapping p orbitals. That means sp2 hybridized atoms. It has to be a ring, and it has to then be planar, right? If everything is sp2 hybridized, it needs to be completely flat so that all of those p orbitals can be overlapping, okay? And so there's a lot of criteria there in that first statement, fully conjugated with overlapping p orbitals. So it has to be planar to be fully conjugated. It has to have sp2 hybridization because it has to have p orbitals, and therefore, and also it needs to have a ring. Now, we have to meet the Huckel rule, which says that an odd number of electron pairs needs to exist in this fully conjugated ring system, or 4n plus 2 equals the total number of electrons, where n equals 0, 1, 2, 3, 4. N is a whole number, okay? This is how we get an odd number of electron pairs. I like using the 4n plus 2 rule rather than the odd number thing, but let's go ahead and look at these two that do not meet the Huckel criteria, okay? Cyclobutadiene first. It is a ring, it is all sp2 hybridized, and it is planar, but it has 4 electrons, 4 p electrons. You can also call this pi electrons if you wish, right? They're electrons in a p orbital. Does that equal 4n plus 2 when n is a whole number? Well, let's do the math. Subtract 2, n equals 1/2. Nope, not aromatic. We're going to learn a different rule that shows why cyclobutadiene is actually not reactive at all, the same way that cyclooctatriene is, right? Why cyclobutadiene is in a totally different category. So let's move on to cyclooctatriene first with the Huckel rule and the aromatic criteria, and then we'll go back to cyclobutadiene in a second. So cyclooctatetraene, when we're looking at cyclooctatetraene, what we want to be able to say is, again, 2, 4, 6, 8, right? Does not follow that 4n plus 2 rule, right? Because n would equal 3/2, not aromatic. One interesting thing about cyclooctatetraene, though, is it is not planar. It is actually, looks kind of like an envelope. So it reacts like a normal alkene because it does not meet either criteria 1 or 2, okay? What's up with cyclobutadiene is that it actually is planar, it is a ring, and it is all sp2 hybridized. But because it doesn't meet the Huckel criteria, it actually meets the 4n rule for the number of p electrons. And what this rule follows, if your number of p electrons is even number of electron pairs, right, 4n, then you are what we call anti-aromatic, highly reactive, all right? Let's take a moment to just talk a few more examples. This is naphthalene. It is a polycyclic aromatic hydrocarbon, but let's prove it, okay? It is planar. It is a ring. It is fully conjugated. There are no atoms that are not sp2 hybridized. Let's count up the electrons. 2, 4, 6, 8, 10 p electrons and plug it into 4n plus 2. Do the math. N equals 2. Check mark. It's aromatic. Awesome. One little change. Let's do that. This is what we call not aromatic. Why is it not aromatic? Well, because right here we have sp3 hybridized carbons. So the molecule itself is not going to be fully conjugated. Okay? Last one before we move on. We don't have to have 6-membered rings, right? Here we have sp2 hybridization, right? Every atom is, even a carbocation is sp2 hybridized. We have 2, 4 pi electrons. That does not follow the 4n plus 2 rule. Nope. Let's try the 4n rule. If n is a whole number for the 4n rule, then our compound is anti-aromatic. Anti-aromatic compounds are highly unstable. So what we see here is that we have 3 classes of compounds. Aromatic, which follows the 4n plus 2 rule. Fully conjugated, planar, and a ring. Those are very, very stable. If you do not follow criteria 1, if you are not planar, not a ring, or not fully conjugated, you are normal, vanilla old alkene, right? Not aromatic. If you are planar, you are a ring, and you are fully conjugated, but you follow the 4n rule for your number of p electrons, you are highly unstable, anti-aromatic. All right, we can explain why this is the case, why we have the Huckel rule with using MO theory. All right, just like before when we talked about benzene and how its homo bonding orbitals are fully complete and all of the antibonding orbitals are unfilled, we'll look at the cyclobutadiene here. Notice how it has non-bonding orbitals, non-bonding MOs. They're in the middle, so they're not lowest energy, they're not highest energy. This lacks a closed electron shell configuration, and that's why it's unstable. That's why it's anti-aromatic. Cyclooctatriene suggests that it would be anti-aromatic as well. However, it forms this tub shape that we know is not planar. So what happens with this actual tub shape is it's adopting this tub shape to avoid being anti-aromatic, all right? Cyclobutadiene cannot do this because it's not big enough. So cyclooctatetraene can form this tub shape so that there's lack of conjugation around those 8 p orbitals, right? So the conjugation does not extend around the entire ring. So the system is neither anti-aromatic or aromatic. It's just not aromatic, or what the book calls non-aromatic. What we want to learn from that is the idea that molecules will avoid being anti-aromatic at all costs. And if a molecule can become aromatic, it will do so, right? Aromatic is what the molecule wants to be because, again, molecules strive to be as stable as possible, okay? Now we can use Frost circles to predict the relative MO energies. These are a very simple way without having to draw all of the MOs or understanding any of those nodes or the phases. Frost circles have a 5-step process. You start with drawing a circle. Hopefully we can do that. Let's practice circles, okay? Then you inscribe the polygon that the shape of the molecule actually is. So if it's benzene, it's a 6-membered ring, right? That is a hexagon, right? I know it's hard to think about our polygons. A hexagon. If you're a pentane or a cyclopentane, then you're a pentagon. If you're a heptagon, right? Because you're heptane, look, this is 7. And we would inscribe it, put it inside. That's what inscribe means. Then draw a horizontal line at each point of intersection for every carbon. If you're fully conjugated, right? If you have a p orbital there, then you have 6. Then you have 7 points of intersection, okay? And those points of intersection are actually the MOs. You draw a line right in the middle, right in the middle. The higher energies are your antibonding, the lower energies are your bonding. Frost circles can help explain the 4n+2 rule because we can quickly and efficiently write out all of our antibonding and bonding orbitals. You can use this as a cheat sheet. The number of bonding orbitals and non-bonding orbitals and antibonding orbitals are listed there, okay? Right? Note that the number of bonding orbitals is always an odd number for aromatic compounds, right? So that's why we want to see those filled, okay? So here's our rules again, just to review. Aromatic compounds fulfill both criteria. A fully conjugated ring with overlapping p orbitals meets the Huckel criteria of 4n+2. Anti-aromatic fulfill the first one, fully conjugated ring with overlapping p orbitals, but it follows the 4n rule. When a compound fails to meet criteria 1, it's non-aromatic. Lowest in energy is aromatic. Highest energy is anti-aromatic. Middle energy is non-aromatic. Now, when we have other types of rings, things like heterocycles, what we want to be able to think about is the lone pairs on that heteroatom could participate in aromaticity, but they do not have to. Take pyridine, for example. Pyridine is a 6-membered ring with one of the atoms being a nitrogen. Now, 2, 4, 6. We already fulfill the Huckel criteria with the double bonds, okay? Aromatic. We do not need this lone electron. Notice that nitrogen already looks sp2 hybridized because it has this double bond right here. So nitrogen is already sp2 hybridized, it has a double bond. If the nitrogen or oxygen or any other heteroatom that we're talking about, if the heteroatom has a lone pair and does not have a double bond directly attached to it, but rather adjacent to it, imagine the resonance that that atom undergoes. Notice how this nitrogen is using its lone pair to be conjugated. All right? And so what that means is that this lone pair, because it is being used in the conjugation, it's being used in the resonance, this lone pair, right? This one right here is not in an hybridized orbital. This lone pair is in a p orbital due to resonance, okay? And that p orbital then says, I can count it towards aromaticity. Pyrrole is also an aromatic compound, has 2 pi bonds and a nitrogen lone pair adding towards its aromaticity. We can see that difference in electron density maps because we see right here, it's localized, the lone pair, not going into resonance. That lone pair is a base. It can go out and pick up anything that it wants in a proton transfer. The lone pair on the parole is actually part of the aromatic ring. It is delocalized, therefore parole is actually not a base. It's not a great base at all, because if that nitrogen gave up that lone pair and went to do a proton transfer, it would actually become non-aromatic, which means higher in energy, which it won't want to do. Polycyclic aromatic hydrocarbons are also aromatic. We saw naphthalene already. It's the smell of mothballs. Super fun. Anthracene and phenanthrene are common polycyclic aromatic hydrocarbons that are products in cigarette smoke, which is also why they're bad not only for the environment, but also for your body. The stabilization energy can be measured by comparing the heats of hydrogenation. So we can see the stabilization energy, the lower the energy per ring, right? Per ring is where we're looking at comparing. These are very, very stable molecules. And so they last a really long time in the environment.